Hello. As we continue Chapter 3, Numbers in the Real World, we're going to talk about Unit 3B, Putting Numbers in Perspective. Let's make sure I got my pen working here. All right, so scientific notation is a format in which a number is expressed as a number between 1 and 10, multiplied by a power of 10. Not really it's a rough thing to define in an exact way for students that don't need to be exact. So we're going to leave it with that. If we take this number, let me see, that's hundreds, thousands, millions, billions, 6,700,000,000 in scientific notation is 6.7 times 10 to the ninth. What we do is we take 3, 6, 9. Excuse me. So we move the decimal 9 places to the left. Positive 9, 6.7. Whereas here we'll go 3, 6, 9, 12, 13, 14, 15. And because the number is smaller than 1, it'll have a negative exponent. If the number is larger than 1 as it starts out, it'll have a positive exponent. Now there's more to this scientific notation, but that's all we need to really know for now. Okay, let's give some meanings to numbers. Some perspective through estimation, one might say. An order of magnitude estimate specifies a broad range of values, usually within 1 or 2 powers of 10. So we'll say they made 34 tens of thousands of dollars, or in the millions, or whatever. Right, we just kind of round it to these larger numbers, so we don't have to get down to the exactness, like 174. Is the total annual ice cream spending in the United States measured in thousands of dollars, millions of dollars, or billions of dollars? It's hard to say, right? So let's say this is the United States, so we're going with like 300 million people. Average person, let's say, has 50 servings of ice cream per year. Let me see. About 4 servings a month. I could get behind that, right? Maybe more in the summer, less in the winter, but whatever. So we have 50 servings per person each year. And we're going to go cheap, just $1 for each serving. And 300 million people. That's 3 times 10 to the 8th. So that's a 3. That's 1, 2, 3, 4, 5, 6, 7, 8. 300 million people. And when we multiply these all out, we'll take a 50 times 3. So 50 times 3 is 150. And we'll still have the 10 to the 8th. But see, this 150 will bring it back 2 places. So now we have 1.5 times 10 to the second power. 10 to the second power times 10 to the 8th power is 10 to the 10th power. Remember, when you're multiplying two things with the same base, you add their exponents. So that's how we get the 1.5 times 10 to the 10th. 3 times 50 is 150. We rewrite that in scientific notation and then multiply by our 10 to the 8th. Here we are. So 10 to the 10th, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, 10 places, and then the decimal. So that's here, here, here. 100,000 million billion. Yep, look at that. I missed it. $15 billion per year, and that's only $1 of a serving. So I know I pay more than that for my ice cream. Okay. Giving meaning to numbers, perspective through comparisons. I want to highlight these two. We're going to use an example with these. Notice that the U.S. annual energy consumption ends in a 10 to the 20th, and so does the world annual energy consumption. The difference here being a 1 versus a 6.3. Okay. And this table gives great examples. Annual energy generation of the sun is more than the world uses in a year, so that's good, right? Energy released by during different things. Energy needed, energy released. Hit pause, check it out. So what we're going to do is we're going to compare the U.S. population to the world population, and then we're going to use the energy consumption to compare the U.S. energy consumption to the world energy consumption. And it's going to say something pretty negative about us Americans. So the world population, let's just go with 8 billion. And 10 to the 9th is billion. 10 to the 6th is million. The U.S. population is 300 million. Now I said 10 to the 6th is millions, but since it's these two zeros, add the other two to go to 10 to the 8th here. My dog's barking, and I'm about to yell at her. I might pause first, but probably not because pause isn't on the screen. So what we're going to look at, compare them. The U.S. compared to the world. That's 3 times 10 to the 8th, divided by 8 times 10 to the 9th, people. So that's 3 divided by 8, 3/8, and then our times is 10 to the 8th divided by 10 to the 9th. When you're dividing two things with the same base, you subtract their exponents. 8 minus 9 leaves us with a -1. 3/8 is 0.375. 10 to the -1 says move the decimal one more place. Nope. Move the decimal one more place. There we go. So we'll have 0.0375. And that's just for the 10 to the -1. We move here. But now to get a percent uses 2 decimal places, 3.75%. So the U.S. is only 3.75% of the entire world population. We're nothing, right? U.S. population is only about 4%, 3.75 of the world's population, but as shown in table 3.1, the United States uses about 1 times 10 to the 20th energy, and the rest of the world uses 6.3 times 10 to the 20th. I don't remember what the units were that. So 1 divided by 6.3 is about 16% of the world's energy. So Americans use more than 4 times as much energy per person as the world average. Yeah, we're to blame. We have a large responsibility in this idea. Let's look at perspective through scaling. We see this a lot on maps. Verbally, we might say 1 centimeter is equal to 1 kilometer. Graphically, if we take a centimeter, we have a full kilometer on our map, right? And this is free in order to represent maps. This is what we'll do. We'll always scale them. As a ratio, we'll say 1 centimeter is 1 kilometer. It means a ratio of 1 to 100,000. Now, how is that? Okay, so 1 kilometer is equal to 1,000 meters. Kilo being 1,000, it's 1,000. But centimeters, right? There are 100 centimeters in 1 meter. So I'm going to multiply this number by 100, which means I'm going to tack on 2 zeros. The 3 I had here, the 2 zeros I had here, still a 1 in front. So that tells me from centimeters to kilometers, it's a 1 to 100,000 ratio. All right. Let's look at it. The distance from the Earth to the Sun is about 150 million kilometers. The diameter of the Sun is about 1.4 million kilometers. And the equatorial diameter of the Earth is about 12,760 kilometers. All right, no millions here. Put these numbers in perspective by using a scale model of the solar system with a 1 to 10 billion scale. 1 to 10 billion. Okay. 10 billion is 10 to the 10th. Right? 1 billion would be a 9th to the 9th. But since it's 10, there's an extra digit there. It's 10 to the 10th. That's our billion scale. Here we go. The distance, right? 150 in scientific notation, we'll move it to 2 places along with millions. Millions are 10 to the 6th, plus 2 more is 10 to the 8th. We'll take 1.5 times 10 to the 8th and divide it by 10 to the 10th. We'll leave our 1.5. We'll have our times. Dividing two things with the same base, we'll subtract. 8 minus 10 is a -2. But then here, this is a conversion. 1.5 times 10 to the -2 is 0.0215. Now, 0.015 kilometers, can you tell me how far that is? Nah. So what we're going to do is we're going to take 1,000 meters is the same as 1 kilometer. And that's what we're doing here. We're going to multiply by 10 to the third because that's how many meters are in 1 kilometer. 10 to the third meters in 1 kilometer. 10 to the third times 10 to the negative 2. When you're multiplying two things with the same base, you're going to add their exponents. That's 1. 1.5 times 10 to the first. We move the decimal one place and we'll have 15 meters. All right, so the distance from the Earth to the Sun is going to be 15 meters in our scale model. Note that in the last step we converted the distance from kilometers to meters. We'll do the same now for the Sun and the Earth, all right, for the sizes of their diameters. So we know they're 15 meters apart. The actual Sun's diameter is 1.4 times 10 to the 6 kilometers. We'll keep our 1.4. 10 to the 6 divided by 10 to the 10th. If you divide two things, the same base, you subtract their exponents, we'll get a negative 4. We'll go from centimeters to centimeters to kilometers. Right here, that's 10 to the 5th. 10 to the 5th is 100,000 centimeters in 1 kilometer because, again, 0.01234, right? 0.00014 kilometers is pretty tiny, but 14 centimeters, we can measure that. We actually have tools. The actual Earth diameter is 1.276 times 10 to the 4th. 1.276 times 10 to the negative 6, right? Because we subtracted our exponents. Converting millimeters to kilometers is an extra power of 10 from centimeters. So that's a very, very tiny little Earth. It turns out the model Sun at 14 centimeters in diameter, roughly the size of a grapefruit. The model Earth at about 1.3 millimeters, where's my pen? There we go. 1.3 millimeters is about the size of a ballpoint that's inside a pen, right? A ballpoint pen, that little roller ball, that's how big the Earth would be. Distance between them is 15 meters. All right. $1 billion seems like a lot. And there's a lot of billionaires in our world. So what could they do? Well, one way to put $1 billion into perspective is to ask a question like, how many people can you employ with $1 billion per year? Let's suppose that, these are employees that are being rewarded appropriately for their efforts and $100,000. And it costs the business an additional $100,000 per year in overhead for each employee for office space, computer services, health insurance, the company car, whatever else you got going on, the gym. The total cost of an employee is therefore $200,000. So $1 billion would allow a business, all right, so we'll put 1 billion. Billions are 10 to the 9th. 200,000 per employee, that's 3, 4, 5. 2 times 10 to the 5th per employee. Now, how do we get 5 times 10 to the 3rd? Because it looks to me like we get 1/2, right? There's a 1 always. Times 10 to the negative 4th. But what is 1/2? 1/2 is 0.5. And if I were paying attention, that would be a positive 4, because 9 minus 5 is positive 4. But when we move this decimal one to this direction, we'll take the exponent on the 10 down because we've moved over a place. $1 billion per year could support a workforce of 5,000 employees, each making 100,000 and having 100,000 in bonuses, or what it takes to take care of them. Another way to put $1 billion in perspective also points out how different numbers can be even when they sound very similar. Suppose you become a sports star and earn a salary of $1 million per year. How long would it take you to earn $1 billion? Well, we're going to simply divide 1 billion by your salary of 1 million per year. And look, all right, 1 billion is times 10 to the 9th. 1 million is times 10 to the 6th. 9 minus 6 is 10 to the 3rd. Right? The dollars cancel out. 10 to the third years, well, that's a 1 followed by 3 zeros, 1,000 years. So even at a salary of $1 million per year, earning $1 billion would take 1,000 years. I don't see why we can't pay public school teachers, I don't know, maybe community college and university faculty $1 million a year. It'd take thousands of years to earn $1 billion. All right. Relative size, right? It's a little bit of scientific notation. I'm going to put a link in the description to take you to more on scientific notation in case you need it. Thanks for watching.